Hi, I'm Yana Smith. I'm working on robotic assemblers for discrete lattice structures. Discretizing a lattice structure into repeating blocks, or voxels, enables the assembly of varied high-performance architectures using the same voxel feedstock. Selectively varying voxel types can introduce tuned metamaterial behavior in the overall structure, for example, selectively compliant regions. To automate the construction of larger-scale voxel structures, we want to use swarms of relatively simple robots that are able to traverse the structure and place new blocks of material. I wanted to use this class project as an opportunity to explore some variations of this type of system and methods for having robots collaboratively manipulate objects. I have a set of 3 modules, a wrist-style actuator, an elbow-style actuator, and an unactuated voxel. These can be assembled in Drake to form a variety of different robot configurations. I am using this 5 degree of freedom assembly as the basic robot. It has 2 elbow-style joints, 3 wrist-style joints, and 2 gripper feet, which I am defining as the bottom face of the terminal voxels. In the actual physical robotic system, the connection between the robot and the voxel structure will be made with some sort of on-off system, for example, using electropermanent magnets. For this project, I am modeling these connections as welded joints in Drake. This means that the condition for a successful grab is just that the gripper face of the robot makes contact with the target gripping face. Let's look at a motivating scenario where the robot needs to collaborate to achieve the desired goal. I have 2 identical robots and a 1x2 voxel stack. The robots need to move the voxel stack to the other side of the divide, which is a wider gap than they can individually traverse. To do this, Robot 1 picks up the voxel and passes it to Robot 2. They readjust their position so that Robot 1 can grab the opposite face of the voxel. Robot 2 releases from the ground and is swung to the other side of the divide. Robot 1 lets go of the voxel stack, and Robot 2 places it on the ground. The robots then reattach to each other, and Robot 1 swings Robot 2 back onto the original platform. In the course of the overall trajectory, joints are welded and unwelded a lot. To accommodate this, I split the overall motion of the robot into many subsections that are structured fairly similarly. Let's look at the first handoff as an example workflow. The multi-body plant consists of the robots, which are welded to the floor, and the voxel stack that is welded to Robot 1. The initial positions are set using the final positions from the simulation of the prior segment. Drake's InverseKinematics method is used to solve for the joint configuration that satisfies the given constraints and costs. This process for generating the initial and final positions is used for every motion segment, with occasional changes in formulation, usually in terms of using cost versus constraints. Next, I find a trajectory between these points. I tried out a few different strategies for this, but here I use DirectCollocation with the collision-free versions of the geometry, and enforce the initial and final states as constraints as well as joint limits, and use proxies for no collision constraints. I take the state trajectory from this, and feed it into the Inverse Dynamics PID controller, and then run the simulation forward. From there, we advance on to the next segment of the motion. Another formulation I used for creating the trajectory is running InverseKinematics on offset points from the target to make a set of keyframes that the robot then advances through. I like this workflow and may switch it in for all the motion segments. I would like to be able to adapt this project so that I can use it as a tool for generating trajectories in joint space that I can then run on a hardware version. Thank you for watching, and thanks to the course staff for a great semester.